Hello everyone, I'm Mikhail Golovnya, Senior Scientist at Salford Systems, and what I'm going to show you today is a quick set of steps how to build a regression model using MARS. MARS stands for Multivariate Adaptive Regression Splines. It was developed by Jerome Friedman at Stanford University back in early 90s. There is a very comprehensive paper that describes all of the mathematical and statistical foundations of MARS. But what we'll do today, we will just use SPM and try to build a regression model to highlight some of the key principles and also the simple sequence of steps needed to do that. So let me go into SPM. I have Salford Predictive Modeler 7.0 open up. In order to build a regression model, of course, we need a data set. So what I will do here, I'll proceed by clicking the open icon. And I'll pick Boston housing data set, a fairly well-known data set that has to do with predictive house values in Boston area back in 1970s. You may find more details on the data set if you search the literature out there and some supportive documentation. Notice that we support a bunch of different file formats. For example, I click on the files of type, and in addition to ASCII, I have all sorts of other fairly well-known and popular statistical formats on the list. In my case, ASCII is the most convenient, and notice that I'm looking on my D drive in the training folder. Of course, in your case, you're likely to have data sets located in a different location. So click on boston.csv, click open. Notice we have 506 observations, 14 variables. Now I am going straight into the modeling side. Clicked on the model button. The model setup window opens up. And here notice my analysis method is now set to MARS. Now SPM offers a whole bunch of different data mining approaches, and in this case we're focusing on MARS, and specifically on the regression side of MARS, which models continuous response variables. Here in this part of the window, I have a list of all available variables in the data set. And sometimes it's useful to sort it in file order, which is what I will do here. The very last variable on the list is the variable that we want to predict, and that's the median value on home values back in Boston, about 1970s. The remaining variables will serve as predictors. So I'm highlighting these, and I click Select Predictors. And again, we're working on the regression side, and this is going to be a MARS modeling. Now, the next thing that we normally set, other than specifying target and predictors, we need to decide how we're going to validate our model performance, or how we're going to choose the optimal model in the end. Now, MARS has a number of different modes. I will describe some of them in follow-up videos. For now, the simplest one is the fraction of cases selected at random for testing. Now, in this case, I will essentially ask MARS to take a random sample, about 20% of the original 506 observations, set it aside as a test sample, and use the remaining 400 or so records to build a number of different models, and then evaluate their performance on this independent test sample. Now, MARS itself also has a number of engine-specific settings, and those are concentrated under Options and Limits tab. Most of these settings can be left alone, at least for this initial round. But one setting that I always find beneficial to change is the max number of basis functions, which in this case I will increase up to 30. The actual number of these is subject to consideration, and you may want to play around with different settings to see which number of basis functions gives you the most acceptable results. Now, 30 is a good starting point. You can increase it up to 100, maybe 200, but certainly no more than that, because then you may run into some computational difficulties and the lengthy run times. Also notice that for the purposes of this demonstration, I'm not going to include interactions, so the maximum interactions is set to default values of 1. Okay, so again, to summarize, I picked my target, I picked my predictors, I set the testing method, and I specified that I'm trying to run up to 30 different basis functions in order to build a regression model in Mars. At this point, I'm ready to hit the Start button, so I'm pressing Start. And as you can see, almost instantaneously, Mars comes back with the overall summary of this current modeling iteration. So in particular, you see the basis functions being added one at a time. And even though I've requested up to 30 basis functions, internally Mars decided to stop once it added 24 basis functions due to some potential collinearity issues. You also see two curves, the learned performance in terms of mean squared error shown in blue curve, and it obviously as the model gets larger and larger, the learned performance gets better and better. And the red curve corresponds to the test mean squared error, and the test is that 20% test sample that we set aside initially. As you can see on the test sample, initially model learns quite a bit, and it kind of flattens out and even gets worse as the model pushed into the overfitting side with the number of basis functions is more that is necessary. The green beam here shows the model that has the best performance based on that independent test sample. And in this case, it is shown to have 11 basis functions. So we're going to focus at that model for a while, for now, and see what are additional pieces of information that we can extract, and also how we can interpret this model. First of all, if I click on the summary button here, I get access to all sorts of summary displays, out of which the most interesting ones will be, of course, the overall summary that tells me that my R squared on the test sample of the current model is about 76–77%. And notice there is a little bit of overfitting because my learn R squared is way better than test, so we may want to keep an eye on that. The next thing interesting to look at is the variable importance display that shows variables ranked according to their contribution to the overall model predictions. And in this case, variables like LSTAT, which is the percent of low socioeconomic status population in neighborhood, happens to be most important. And not far behind is the variable RM that stands for house size. Now, a little bit of understanding on how Mars works comes from the basis functions tab. So if I click on the basis functions, what you actually see here is the SAS representation of the exact Mars model that was built for you here. Notice that any Mars model has two different parts or two different components. Here, you have definitions of basis functions. And basis functions is essentially a transformation of the original variables. I have variable LSTAT, variable RM, dis, crime, etc. All of these individual variables undergo simple this max, zero, and the difference transformations to construct a new set of variables known as basis functions. And once basis functions have been constructed, the rest of the modeling equation looks as if you had a multiple linear regression constructed around these basis functions. So Mars is one of the few tools that we have that off the bat gives you a very simple description of the model that you constructed that is very close to classical regression approaches. So you actually see the equation that you can drop in elsewhere and use it as your modeling description. However, Mars also gives you better ideas on how these individual variables are combined. Like if you notice in this equation here, we have different basis functions based on different originating variables. So if I were to combine all basis functions that are based on variable LSTAT, and this will be basis function 1, basis function 2, and that's pretty much it. So if I take those two terms and look at them as one single transformation, then I could plot it and see how variable LSTAT contributes to overall model prediction. Now the good news is you don't have to do it by hand, because all of that is already done for you by Mars, and access to that information is located under Curves and Surfaces tab. Here, Curves and Surfaces shows the list of all important variables, and if I click on these one at a time, I can see the joint result of combining basis functions that are originating on the variable of interest. Now, we have already noticed that LSTAT has two basis functions in the basis functions code. If you took those two basis functions along with the coefficients in the regression equation and plot the result, then you'll see that the contribution looks like this. In other words, LSTAT has a much steeper slope in the beginning, and then at a certain point, somewhere around 6 or 7, that slope changes to a more gradual decline. Similarly, you can look at all of the other variables. You can look at the variable RM, for example, that shows that there is no contribution up until about 6.3. And then from that point on, there is this positive contribution associated with the impact of variable RM or the house size onto the overall value of home. Now, in a similar way, you can study all of the remaining variables. Now, what is very interesting about all of these displays is that they exhibit what we call a nonlinear behavior. In other words, instead of hitting a straight line that spans across the entire range, Mars figured out automatically, without any particular assumptions or user intervention, the best optimal places to place these so-called knots that indicate the changing behavior in the response surface, like this variable distance that indicates distance to employment centers in miles. Shows that in the very beginning, within the city center, you have a very drastic change attributable to that variable with respect to house values. But once you go into 2, 3, 4 miles outside, the contribution of that variable somewhat diminishes. So, and those are the typical insights that you can get from running Mars. So, as you have seen, without knowing all of the intricacies of Mars and all of the statistical kind of machinery that happens underneath, it is relatively straightforward to build a simple model and find an interesting answers to whatever phenomenon that you're studying. Now, what Mars allows you to see is, by looking straight into the data set, it extracts possible nonlinear patterns. It also highlights which variables are most influential and how the variables need to be transformed in order to obtain better predictions. And as I have said before, you don't have to supply any specific modeling assumptions. So you don't have to know exactly which variables are important, which are not. And you can let Mars do all of that discovery for you. And then by studying and analyzing the resulting plots and graphs and performance measures, you can actually see what those transformations look like. Another big advantage of Mars is that the end model, as we saw here, is very straightforward. It fits on one screen, and it can be easily presented as a conventional statistical equation. And sometimes that alone could be a very beneficial and very useful feature for some of our users. That's it. That's everything what I wanted to show today, and in the follow-up videos we can expand on some of the specific applications of Mars.